The next is the nucleophilic substitution reactions, the mechanism of nucleophilic substitution reaction. That is the mechanism, that is the nucleophilic substitution reaction followed by two types of mechanism are called sn2 mechanism and sn1 mechanism. sn2 and sn1 mechanism. sn2 mechanism means it is bimolecular nucleophilic substitution reaction, and sn1 means unimolecular nucleophilic substitution reactions. Okay. We know the molecules are of three-dimensional structure. The stereospecificity of nucleophilic substitution reactions of haloalkanes can be exemplified by taking the sn2 reaction of chloromethane with the hydroxide ion, and here the chloromethane, the sp3 hybridized chloromethane, is tetrahedral in shape, and when the hydroxide ion attack this chloromethane, it can approach the chloromethane to the opposite side of the chloride ion attached to the carbon, and therefore first there form a partial bonding with the oxygen of the hydroxide ion with the carbon, and also the leaving chloride ion also have a partial bond with the carbon, and therefore the produced alcohol have an inverted configuration of the parent chloromethane, because the hydroxide ion approach the chloromethane just opposite from the leaving chloride ion. This transition state is not stable and cannot separate from the reaction mixture, and as soon as this transition state formed, the chloride leaved from the transition state and methanol regained. Here the slowest step, both chloromethane and hydroxide, the nucleophile, participate the reaction, and therefore it is a second order kinetics, and therefore the name bimolecular nucleophilic substitution reaction or sn2 reaction. Now thus the sn2 mechanism followed more by the methyl halides than the primary halides, than secondary halides, than tertiary halides. That is, the next is sn1 mechanism, unimolecular nucleophilic substitution reaction. This mechanism can explain by taking the tertiary butyl chloride as an example, that is the nucleophilic substitution of tertiary butyl chloride with the hydroxide ion. Tertiary butyl chloride. There are bulky methyl groups attached to the carbon to which the chloride is bonded. Therefore, the approach of the nucleophile, the approach of the nucleophilic OH- ion hindered by the presence of the bulky methyl groups, and therefore there is no formation of a transition state, a unstable transition state, but the first step is the cleavage of CCl bond, tertiary butyl chloride, to form a carbocationic site, tertiary butyl carbocation. And this tertiary butyl carbocation, after leaving the chloride ion, is almost in planar structure, and therefore the approached hydroxide ion, the approaching nucleophile, can attack this carbocationic site from either side of the leaving group, that is through the same side as the chloride is removed or from the opposite side of the chloride group, and therefore there is a possibility of inversion of configuration and also retention of configuration. Okay, and therefore there is two types of configuration. That is, in case of this, the OH bond is bonded downwards, and there is another chance as a mirror image of this as the OH minus bonded upwards.
In case of sn1 mechanism, as we see, the tertiary alkyl groups, tertiary alkyl halides mostly undergo sn1 mechanism, then secondary, then primary, then methyl chloride. By the same reason, the allylic and benzylic halides also undergo sn1 mechanism. For example, in case of this allylic halide, allylic chloride, the reaction with an nucleophile OH minus, first this undergoes a cleavage of carbon chloride bond, to form CH2 double bond CH2 with a carbocationic site with the cleavage of, that is the leaving the chloride. And this carbocationic site is stabilized by resonance effect. Stabilized by resonance effect. That is, it can be of the resonance structure or as the double bond can be shifted here to here, and the positive side shifted to this carbon, and therefore it can be represented as CH2 double bond CH2 with a double bond. Okay, that is, there is a possibility of a stabilization through resonance after the cleavage of this carbon chlorine bond, and therefore it undergoes first sn1 mechanism rather than the sn2 mechanism. That is, the attack of OH minus takes place after the carbocationic site is formed, and it follows a sn1 mechanism rather than sn2 mechanism. Allylic halides undergoes sn1 mechanism for the nucleophilic substitution reaction. In case of benzylic halides also, that is CH2CO. Benzylic halides also, first the carbon chlorine bond is break and forms a carbocationic site here, that is CH2 with a positive charge with the chloride. And this carbocationic site is stabilized. By this CH2 with a positive charge. Can be stabilized by the shifting of this double bond, the double bonded electrons, and forms as double bond CH2 with the positive charge here. And now there is a shifting of double bond to this side, this carbon-carbon bond, and now the bond double bond CH2, here the double bond, now the positive side here, and shifting of this double bond to this carbon-carbon bond. Now the resonance structure can be drawn as double bond, this CH2, here the double bond, and therefore the positive side here. Now the double bond shifted to this side, and now structure can be written as CH2 with the positive charge. Here the double bond. Okay, that is, there is a stabilization. Resonance effect കാരണം ഒരു stabilization സാധ്യമാണ്. Number of resonance structures increase ചെയ്യുന്നതിനനുസരിച്ച് stability കൂടും. And therefore, by the resonance effect, the carbocationic site is stabilized. And therefore, after the carbocationic site is formed, then only the attack of the nucleophile take place, and therefore this benzylic halides also undergoes sn1 mechanism for the nucleophilic substitution reaction rather than sn2 mechanism. And it is also by the presence of this bulky benzene ring, the coming nucleophile cannot easily attack the carbon to which the chlorine is attached, and therefore it undergoes first the cleavage of carbon Cl bond, carbon chlorine bond to form the carbocationic site. Okay.